Use the graph of y equals the square root of x to graph g of x equals the square root of x minus 2. Since x has been replaced by x minus 2, the graph will be moved 2 units to the right. 0, 0 will go to 2, 0. 1, 1 will go to 3, 1. And 4, 2 will go to 6, 2. So the curve would look like this. And it's actually a rigid transformation or translation of the original 2 units to the right. It appears as if it contains the point 2, 0, 3, 1, and 6, 2. We can use a table of values to give us more confidence in the graph that we've drawn for y equals the square root of the quantity x minus 2. We'll use the values 2 and 3 and 6 for the x values. Then for y, we'll get the square root of 0, the square root of 1, and the square root of 4, respectively. So we confirm that 2 goes to 0, 3 goes to 1, and 6 goes to 2. Notice that if f of x is the square root of x, its domain is the half-closed interval from 0 to infinity, includes the 0. And g of x equals the square root of the quantity x minus 2 will have a different domain. Since all the points have been moved 2 to the right, its domain is the half-closed interval 2 to infinity. This might remind you of some work that we've done with composition of functions. Note, if I add the function h of x equals x minus 2, then you can see that g of x is the same as f of h of x. So g is the composite function of f with h. Here h is called the inner function. It's the one that acts on x first, and an inner function affects the x values, and in this case affected the domain, you'll notice. In the second example, we are going to again start with y equals the square root of x, and this time we're going to graph y equals that square root of x plus 3. So the square root of x is intact this time, and this means that we're going to be moving the graph 3 up. So 0, 0 goes up to 3, 0, 3, 1, 1 goes up to 1, 4, and 4, 2 goes up to 4, 5. The new graph would look something like this. This time all the y's have had 3 added to them to get the points 0, 3, 1, 4, and 4, 5. Checking with the table of values for y equals the quantity the square root of x plus 3, and using 0, 1, and 4, we get the square root of 0 plus 3, the square root of 1 plus 3, and the square root of 4 plus 3, respectively. So 0 goes to 0, 1 goes to 4, and 4 goes to 5, as was suggested. This time, notice that f of x equals the square root of x, and g of x equals the square root of x plus 3 have the same domain, but their ranges are going to be different. The range of f of x is the half-closed interval from 0 to infinity, whereas the range of g is the half-closed interval from 3 to infinity. In order to look at this as a composition of functions, this time I'll let h of x equal x plus 3, and this time g of x is equal to h of f of x. So g is the same as the composite function h with f, where h is now the outer function. And the effect when we take a composition and the outer function is x plus 3 is that the y values will be affected. This time, all the y values have 3 added to them. Moving to the next example, it's a two-step process. We start again with y equals the square root of x. Then we go to y equals the square root of the quantity x plus 5. And finally, to y equals the square root of the quantity x plus 5 minus 3. So when x has been replaced by x plus 5, we're going to move 5 to the left. And in the second part, the square root of x plus 5 is intact, so its graph will be moved 3 down because we have the square root of the quantity x plus 5 subtract 3. So we're going to move each of the points 5 to the left and 3 down. That's going to give us -5, -3, -1, -2, and -1, -1. Now the graph, by connecting the points, will look something like this. The graph has, of the original function, y equals the square root of x, has been moved 5 to the left and 3 down. Again, a table of values will confirm and the x values I'll use this time are -5, 4 and negative 1. I see that I made a mistake when I labeled the second point over here. It should have been negative 4, negative 2. So now, when we substitute those x values, we're going to get the square root of 0 minus 3, the square root of 1 minus 3, and the square root of 4 minus 3, respectively. So negative 5 goes with negative 3, negative 4 goes with negative 2, and negative 1 goes with negative 1. Note that here for G, the domain is going to be all values of x greater than or equal to negative 5, and the range is going to be all values of y greater than or equal to negative 3. In the fourth example, starting with y equals the square root of x, again, 2 steps. First of all, we'll go to y equals the opposite of the square root of x, and then y equals the opposite of the square root of x plus 1. So in the first step, the square root of x has been multiplied by a negative 1. The square root of x is intact, but it's been multiplied by negative 1. This reflects the graph over the x-axis, reflects it vertically. In the second step, the opposite of the square root of x is intact, but 1 has been added. This is going to move that graph 1 up. So this time I'm going to start with the 4, 2, reflect it over the x-axis, and then move it up 1. For 1, 1, I reflect it and move it up 1. And when I reflect 0, 0, it stays exactly where it is, but we move up 1. So the points in our final curve can be connected to give this graph. It has the points 0, 1, 1, 0, and 4, negative 1. Notice if I were to connect the points after the reflection, we would see, first of all, we reflected, and then we moved up 1. So, table of values, going to y, going to the opposite of the square root of x plus 1. I'll use the x values 0, 1, and 4. So we get the opposite of the square root of 0 plus 1. 0 goes with 1. We get the opposite of the square root of 1 plus 1. 1 goes to 0. Negative 1 plus 1. For 4, we get the opposite of the square root of 4 plus 1. That's negative 2 plus 1, which is negative 1, which confirms what we had before.